Okay, we're going to use this applet called definite integral. I'm going to set the sliders a to 0, b to 4, n is 2, and the function's already set as x squared. So n is here, so select that to 2. Just remind ourselves what we're going to do. A is 0, b is 4. A is 0, b is 4. So we've set those. This is A, and this is B. Okay, we're going to tick the lower checkbox and record the error and explain what we notice. Check the lower one. Okay, and what we see here is 1 square. This is a gross underestimate of the actual area, because the actual area is that one there. And then if we do that one, here we get 2, and take that one off. And here we've got this end touching of the rectangle touching the curve, and when we do the other one, we have the other side of the rectangle. This is a gross underestimate of the area. Now if we repeat it for different values of n, and you can fill in this table, the lower area, the actual area, and the upper area. So if I go back to the applet, and let's make n a bit bigger, let's make it 10. If it's lower here, remember this is where they touch on this side, and we check that, and that's the actual area, and there is the upper one. If we select both, we can see both sets of rectangle. See one rectangle here, one underestimating and one overestimating the actual area here. If we click these, you get the value for that particular. If you sum up all the green ones, or the lower ones, you'll get 18.24. In this case, you sum up all the blue ones, you'll get 24.64, whereas the actual area is 21.33. This is how this applet works. Okay, you need to explain what happens as n gets larger. So it says here, set A is 2, and B is 2.5, and n is equal to 1, and draw a diagram on square paper and see what you notice. Let's have a go at that. So A is 2, B is 2.5, and n was 1. So n is equal to 1. Okay, so what you need to do is draw that on paper and see what you notice. So we're going to look at that in more detail. So what you should have noticed is something like this. It's just flip back and forth. You can see here you have 1, 2, 3, 4 for the lower rectangle, and here you have 1, 2, 3, 4 for the upper rectangle, and the shaded red bit actually represents the area. Right, so what you need to do is put some labels on. You can label this one A, this B, this E, this F, this D, and this C. And we're going to call this a little bit of X, so we'll call it delta X is the mathematical term, but you can think of it as a little bit of X. This will be the value of the Y coordinate of the curve at this particular point, but this point here will be the Y coordinate, the original Y coordinate, plus a little bit of Y. and this is what happens. Write down the area of the rectangle ABEF, so that's going to be y times delta x. Now write down an expression for this times this, the larger rectangle, and that's going to be y plus delta y times delta x. We're trying to find the area. Now complete this statement. The actual area, the shaded bit, will be between y delta x and y plus delta y times delta x. Now, as n increase, what will happen to the delta x and the delta y? Let's go back and put the applet for that. Let's make n bigger, and let's make this be for more values from 0 to, let's say, to 4, which will fit in nicely. Okay, so there we have n is 15. What we can notice here, if we take n up to 20, this error, this underestimate and this overestimate is actually going to decrease. If I increase it up to, let's say, 40, it gets even smaller. And then if I increase it up to the maximum amount on this applet, will be 50. Obviously, we can carry on. And what we're doing here is making the width of the rectangles very, very, very small. In fact, what we do, we'll make it actually infinitely small. If we look at the actual areas, this is the lower area, this is the upper area, this is the actual area. You can see that these two are between either side of the actual area. One's slightly bigger and one is slightly smaller. And obviously what happens is, as you increase the number of rectangles, the area actually gets squeezed between the two of them, and it will actually become the actual area. You have to take an infinite number of rectangles to do that. And what you're doing in integration is you're just summing up all the areas of those rectangles. So increasing the number of rectangles implies that delta x goes to 0. Also delta y will become 0. So this width here will become very, very small, and this width will become very, very small. So what you're actually doing, the little bit of area will actually be squeezed between the two same things, because the delta y will be actually 0. And therefore you can say that if you divide this by delta x, you get that the little bit of the area divided by the little bit of x will be between two things that you actually know. Now from differentiation you need to know this, so obviously, and there's actually a slight mistake there, it should be delta x goes to 0. The limit as delta x goes to 0, delta a over delta x will become dA over dx. And the opposite of differentiating, so we know that dA by dx would be equal to y, and the opposite of differentiating is to integrate. This is why area underneath the curve is actually represented by integrating the curve. Obviously you have to integrate between two values. If you integrate between a and b on our applet, so going back to our applet, a would be equal to 0 and b would be equal to 4 in this case. Of x to the n dx, you get x to the n plus 1 over n plus 1 from a to b, provided that n is not equal to minus 1.